Jupiter is loud. Not to your ears, but to a radio receiver, it screams louder than any planet in this solar system. Lightning storms bigger than Earth itself rip through its atmosphere, and the resulting bursts of radio energy are so intense that early radio astronomers mistook them for interference in their own equipment. But what's even crazier is that Jupiter isn't broadcasting because it wants to be heard. It's broadcasting because it can't help it. Every planet, every star, every collapsing husk of matter in this universe is leaking sound into the void, whether it means to or not. The sun does the same thing, only softer. Solar wind, the constant stream of charged particles pouring off its surface, generates a low static hiss that radio telescopes have picked up for decades. It sounds almost peaceful, like distant rain. But that hiss is a warning as much as a whisper. It's the sound of a star losing 1,000,000 tons of itself every second, forever. Even our own planet is not silent. Earth's magnetic field bends incoming particles into looping paths that produce a rising, chirping tone scientists call chorus waves, named because early listeners thought it sounded like a flock of birds at dawn. It is not birds. It is the planet itself, ringing like a bell every time it's struck by the sun's breath. But the frequencies get stranger the farther out you go. Pulsars are the collapsed cores of dead stars, spinning up to hundreds of times per second, sweeping a beam of radiation across space like a lighthouse. When that beam crosses Earth, radio telescopes catch a pulse so precise it once made scientists think they had found an alien signal. The first pulsar, discovered in 1967, was nicknamed LGM-1, short for Little Green Men, before anyone understood what it really was. Picture a corpse the size of a city, denser than anything that should exist, spinning fast enough to tear itself apart, and somehow choosing instead to sing. And that leaves us with a question. If a dead star can broadcast with that kind of precision, what happens when something goes wrong? That's where fast radio bursts come in. These are blasts of radio energy that last only a few thousandths of a second, but in that instant, release more energy than the sun produces in an entire year. Most of them come from galaxies, billions of light years away, and most of them are never explained. We catch the signal. We measure the source. We still don't know what caused it. No warning. No repeat. No answer. Here is the unsettling part. Some fast radio bursts do repeat on their own unpredictable schedule, as if something out there is trying again. The leading explanation points to magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. Fields so powerful that a magnetar passing halfway to the moon could theoretically wipe every credit card on the planet. When a magnetar's crust fractures, the result is a starquake, and the sound it makes crossing the galaxy is one of the loudest events physics allows. But even a starquake is a local event. The next kind of broadcast doesn't come from one object. It comes from the space between all of them. In 1977, a radio telescope recorded a signal so unusual, so tightly matched to what scientists expected an artificial transmission to look like, that the printout was circled in red pen and labeled with a single word. Wow! It was never detected again. It has never been explained. And it means that somewhere in the noise of the universe, buried under 1 trillion natural frequencies, there might already be one signal that wasn't natural at all. So what happens when we stop listening for something that sounds like a message and start listening for the universe's own private conversation? In 2003, astronomers pointed a telescope at the center of the Perseus galaxy cluster and detected a note, a real, measurable sound wave rippling outward from a supermassive black hole at its core. It is a B-flat, 57 octaves below middle C, a frequency so low that a human ear could never process it. Even if sound could travel through the vacuum of space, which it cannot. This is a black hole, humming, into the emptiness, forever. The next broadcast isn't a sound at all, not in any sense we're used to. It's a ripple in the shape of space itself. When two black holes spiral into each other and merge, they don't just release energy, they physically stretch and compress the fabric of the universe, sending a wave outward that passes through every planet, every star, every atom in its path. In 2015, instruments on Earth detected one of these gravitational waves for the first time, the aftershock of a collision that happened over 1 billion years ago, involving objects tens of times more massive than our Sunday. You were bent, slightly, by that wave. Everyone on Earth was. Nobody felt a thing. But if gravitational waves can carry the memory of a single collision across 1 billion years, what does the memory of the entire universe sound like? That question has an answer, and it's older than any star. The cosmic microwave background is the leftover radiation from the earliest moment the universe became transparent to light, roughly 380,000 years after everything began. It fills every corner of the sky, in every direction, at a temperature of 2.7 Kelvin, just a few degrees above absolute zero. Part of the static on an old analog television was this exact radiation, ancient light from the edge of time itself, landing on an antenna on Earth. It is, in a very real sense, the oldest sound the universe has ever made. If you thought that was as far back as the signals could go, here is where things become strange. In 2023, multiple pulsar timing projects announced they had detected something even larger than individual gravitational waves, a constant, low-frequency background hum stretching across the entire universe, caused by countless pairs of supermassive black holes slowly spiraling toward each other in galaxies everywhere. This isn't one event. It's the combined overlapping sound of an unknown number of collisions happening at once, a background rhythm running underneath everything, likely for the entire history of the cosmos. Space itself may never have been silent. It may only sound quiet because the waves are, individually, too faint to notice, until you add every single one of them together. And somewhere in that combined hum, there is a silence that troubles physicists more than any signal ever could. Roughly 85% of all matter in the universe is thought to be dark matter, and in the decades since it was proposed, it has never once been directly detected, never confirmed to emit a single frequency of anything at all. If dark matter interacts with light or radio waves the way ordinary matter does, we should have heard something by now. We haven't. Either it is broadcasting on a frequency we have no instrument capable of catching, or it isn't broadcasting at all, and an entire majority of the universe is simply choosing not to be found. If you followed the signal this far, from a screaming planet to a humming black hole to a silence that makes up most of existence, this is the part where the pattern breaks entirely. Some physicists working on string theory propose that reality contains up to 9 spatial dimensions, only 3 of which you can perceive, with the rest curled up at scales smaller than an atom. If those extra dimensions exist, some models suggest gravitational waves could leak into them, meaning a portion of every signal ever detected on Earth might be quieter than it should be, because part of its energy is escaping into a direction you cannot see, cannot imagine, and were never built to sense. And that brings us to the final frequency, the one that isn't a frequency at all, but the theoretical absence of every frequency at once. Some physicists believe the universe currently exists in a false vacuum, a low-energy state that feels stable but may not be the lowest energy state actually possible. If a region of space were to tunnel into a true vacuum, the change would not travel as a wave you could detect and prepare for. It would expand outward at the speed of light, meaning the boundary of that change would arrive at the same instant as any warning about it. No pulse, no hum, no static beforehand, just an ordinary moment, and then a different universe, with different laws, expanding forever, with no observer left behind to measure it. If you've made it this far into every frequency this universe has ever broadcast, from a chattering planet to a background hum spanning all of time, drop a like and subscribe, because the next signal we track down might be the one that finally tells us we were never listening alone. Until then, the universe keeps broadcasting, in a language built from static, starlight, and silence, and somewhere out there, it is still waiting for someone to answer back.